and an activity. Right, so that's what a transaction is here that we want to keep track of, right? And then multiple parties need to understand what kind of transaction is going on, right? They may need visibility just to know that the transaction has happened, and at some point there might also be a requirement for a more forensic analysis of those transactions, right? What kind of transactions are really happening, right? To do that, one more very important part of this puzzle is something called API Setu, right? Where the APIs for various e-governance projects, right, whether are made public, right? So you have access to the test environment using API Setu, and if your project really requires the production level access to those APIs, you can request you can request for a production level access as well, right? So what it is doing is it's enabling our young population to build a large number of next generation applications, mobile apps, e-governance apps, various kind of facilitating applications, right, which is leveraging the data, the infrastructure that is already being built, right? But fundamentally, what this is causing is an exponential growth in the number of digital transactions that are being generated today on a per capita basis, right? We all know that the introduction of mobile phones in the country, it led to a massive penetration of internet, and it really brought the world to our homes, right? But over the last few years, I think we are more and more comfortable in terms of making digital transactions as well as digital payments from our mobile phones itself, right? So it's not just a point of it is just not a one-way traffic where people are viewing information. They're actually starting to produce information on their mobile phones, and we have data that after a few tries, people are comfortable in making UPI payments out of their mobile phones, right? So there is this exponential growth in terms of digital transactions per capita, which is coming from, which has been driven from 2 points, right? One is the number of people who are making these transactions, and secondly, the number of transactions that each individual is doing, right? Today, we don't think, I think in my day-to-day activities, I do not think twice in terms of making a digital payment for, whether it is for an auto rickshaw fare or it is for paying for a cup of tea, right? So these are all very small value transactions, but a large number of them. So eventually I might end up spending, making like 10, 12, 15 transactions on a daily basis, right? Which would not have been possible if I was doing that with a credit card or some other form of payment, right? So it's essentially I'm using these digital transactions as a replacement for cash itself, right? So not only that, right, we are doing these human-to-human transactions, and we are doing machine-to-human transactions as well, because more and more platforms are connecting service providers and consumers, right? We are having these multi-factor authentications which are keeping humans in the loop, right? So we are seeing a lot of these human-to-human transactions, right? As well as we are seeing the emergence of human to machine transactions, right? What I mean by that is, you have NFC based payments that are happening from cell phones, right? You have NFC enabled point of sale devices, right? You have wireless, you have contactless card payment systems. You have payment systems coming in through smart watches as well, right? With WhatsApp Pay, right? So we have a lot of transactions that are generated on a machine-to-machine perspective, right? Where humans are not kept in the, may or may not be kept in the loop, right? So that is also coming in, especially with low latency transactions. So overall, the per capita transactions can only be expected to grow from here on, right? So that's why, because there are so many transactions that are being created, right? How do we create an infrastructure that allows us to manage these transactions effectively, these that allows us to manage this transaction in a form that is where it is it is immutable, right, where these transactions are viewable by the general public if necessary, right, or by the people who need to see those transactions, right? And there is no way of being able to go back and deny a transaction once it has been completed, right? So that's the larger goal from which we have to look at blockchain, right? Before I get into the nitty gritties of blockchain itself, right, let me take out a couple of minutes of saying, going back into the origins of blockchain itself, right? And we have gone through this, I think, in your previous sessions as well, where blockchain itself came out from a desire to avoid these macroeconomic trust erosions, right, which come about because of war, because of geopolitical tensions, because of policy decisions, because of specific foreign policy stands, right? So what's what ended up happening was that we historically these rare events, they have happened, and because of which it has produced these very, very massive macroeconomic shocks, right? Very, very unpredictable because they are very rare, right? And this has all been happening because primarily our currency systems are backed by statute only, right? So in this scenario, we have to take a closer look at what brings about this game of transactions. So it is, whereas I'm talking about this macroeconomic scenario, right? I wanted to take an example of something that is much more trivial, something that is much more personal and much more local, right? So what I'll do is I will probably, all of you are familiar with the game of Monopoly, right? I call it a game of transactions because at the end of the day, what you are doing is a whole series of transactions, right? Everybody has played this game, I believe so, right? But let me set up the game. What's happening is we have four players, right? Arun, Borun, Kiran, and Mala, right? Who are playing a game of Monopoly. And Mala is essentially playing the role of a bank, right? So very familiar example. And all of them are playing with Monopoly money, right? That's what you play Monopoly with Monopoly money, right? Now you can replace that with pretty much any situation where the currency of exchange is local to that set of transactions itself, right? So be it poker, be it if you're playing a game with some other currencies, it does not matter. But at the end of the day, what matters is it's a game. It's got a set of rules, and as each turn is played out, each turn constitutes a transaction, right? So Mala, being the communal bank over here, is responsible for maintaining the account. So she kind of has a ledger where she writes every transaction that is being made, right? So in the first turn, it could be that Mala pays 200 to Arun. In the second turn, Arun lands on one of Borun's spots and pays 150 as rent, right? In the third transaction, Mala pays Borun 200, right, for whatever reason, and so on, right? That's what a ledger is. It's a record of transactions, right? So now the question over here is, what if Mala is biased and is making false entries, right? So because it's a ledger that is maintained by Mala, right, she is the one who is making entries into the ledger, and it is possible that those entries were incorrect, right? So think of the same situation if I were to expand this into a macroeconomic scenario, right? If a bank is maintaining a ledger, right, what is the guarantee that the bank will never make an error, right? Yes, the chances are very, 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 very small, but is it possible? Right? That's the question we are asking over here, right? So this gets us to a very fundamental question about what are ledgers and what is money itself, right? So ledgers, you have all used ledgers in one form or the other, right? What would be the characteristics of a good ledger, right? So a ledger is a record of accounts for economic activity or financial relationships, right? So what are the characteristics of a good ledger? Typically, if you have a ledger, it should be immutable, right? If you are writing something onto the ledger, it should not magically disappear, right? It should be consistent, right? If whatever format or however you are counting a debit transaction or a credit transaction, you should be consistent in your record keeping, right? So typically a ledger should have a timestamp, right? It should have what time that transaction was made, and I'll get into even if we think about a timestamp, timestamp is a very nuanced thing, because what again is consistent time, we'll get into that a little later, right? There should be some ownership. Who has written? Whose ledger is it, right? Who is writing that record, right? It should typically be accurate, right? And it should have an accurate description of a transaction. What am I recording, right? So typically, when you talk about ledgers, you can have personal ledgers, right? Personal ledgers where modifications or updates to that ledger needs a protocol, right? For example, if I am going out for a cup of tea, I can have if I don't want to pay cash every time, I can maintain a running ledger with the shopkeeper, right? So I settle accounts at the end of the day, right? So that's a protocol, right? That's a protocol because both of us understand that the accounts will, we have an unsaid protocol that the accounts will be settled by end of day, right? And therefore the shopkeeper is willing to extend me credit, and I'm keeping track of it, probably mentally, but there is a protocol in place, right? But with institutions, ledgers have to be more formal, right? So of course they are called institutional ledgers, right? And modifications or updates to an institutional ledger would need a payment system, right? Payment system is it could be what is called as a negotiable instrument, like a check, right? Or it could be a non-negotiable instrument, like a bond, like an escrow, right? Where once you have already fixed certain amount for a specific purpose, right? So you came across this in terms of your smart contracts implementation, right? Which were essentially non-negotiables, because a computer does not really have that concept of negotiation, right? It's either the contract is fulfilled by matching all the criterias, or it is not fulfilled, right? So there isn't a lot of gray area in between that, right? Whereas a check, you can request somebody not to deposit a particular check, right? You can request them that deposit it tomorrow, right? There is some amount of negotiable some sort of flexibility around it, right? So but whatever is the thing, institutional ledgers will need some kind of a formal payment system, right? The second thing we have to worry about is money, right? Which in this case acts as a store of value, right? And in this money itself, right, we have something called native currency. Native currency is something that is local within the context of that particular transaction, right? So for example, if we are playing a game of Monopoly, then the monopoly money is the native currency, because all transactions in the game itself is valid with monopoly money, right? On the other hand, if we talk about, I mean, I cannot pay my taxes using monopoly money, right? For that, I will need payment systems, or I will need currency that is accepted for taxes and is represented by central banks, right? So it would be things like banknotes, coins, debts, bonds, legal tender. So this constitutes fiat currency, right? Typically, if we are talking about money, what we are talking about is something like, we expect that the money is durable, right? It is portable, it's divisible, it's acceptable. I can, if I give you a 100 rupee note, you will accept it, right? You will accept it because you acknowledge that you can also buy something worth 100 rupees using that piece of paper, right? So when we that piece of paper is actually backed by statute of the country itself, right? But we have had situations of there been significant monetary shock by changes in the statute itself, right? So that is why people can be wary about using money as the store of value, right? So that said, when we talk about money, we typically expect money to be something that is hard, that has limited supply and is hard to counterfeit, right? So that's very important, because when we want to measure transactions, I think we want a similarish property that it is hard or almost impossible to counterfeit, right? This is where blockchain kind of has a significant parameter, right? So has a significant role to play. Right. So to go back to my previous question of what if Mala is biased and is making these false entries, right? A quick solution would be to say that we need a cryptographically secured ledger without any implicit trust. So big words, we said that we need a cryptographically secured ledger without any implicit trust, so that anybody can believe it, and it, because it is cryptographically secured, nobody can make any changes to it, right? So it is immutable and it has implicit trust. We will come back to that word in a little bit, right? This is what we call as a cryptocurrency. This ledger, which is cryptographically secured, right, is the cryptocurrency. It just so happens that Bitcoin is just the first implementation of a cryptocurrency that addresses trust directly, right? Now, over the last 20 years, right, I think we have had multiple ways to, we have had multiple approaches to try and address this trust issue, right? Including something like HashGold, Hashcash. So there were multiple initiatives that came out from, throughout the late 90s, early 2000s, right? Including cryptocurrency that was backed by gold standards as well, right? But there were protocols which came out which focused on using email as a signature, right? But that was not enough, right? I think it fundamentally these protocols were not able to address that issue of trust propagation. How do you guarantee that there is trust, right? So that's where we were facing an issue. And when Bitcoin came out, right, it came out as a very simple, small 6-page paper by somebody who goes with the pseudonym of Satoshi Nakamoto, right? And a small 6-page paper that talks about a decentralized peer-to-peer electronic cash transfer system, right? That's where it came out from. And if you look at the abstract of the paper itself, it talks about a purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. digital signatures are going to provide part of the solution, but the main benefits of the main benefits are lost if a trusted third party is still required to prevent double spending, right? So they proposed a solution to the double spending problem using a peer-to-peer network, right? The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work, right? So that was very, very important. That's the birth of essentially a data structure called a data structure like the blockchain, right? If I go into the rest of the abstract, you will find a lot of technical terms. I was talking about peer-to-peer electronic cash. It's talking about digital signatures, timestamps, double spending. I'll get into each of them, right? Hash-based proof of work, chain of proof of work, longest chains. So it's talking about a lot of them, but the only non-technical term that you really find over there is financial institution, right? And while it is using the word financial institution, the implication is that there should be no unnecessary intermediary, because that intermediary can become a point of failure, right? So in creating blockchain, in creating Bitcoin, inadvertently what got created was this technology called blockchain, right? Which is making certain guarantees, right? How is it making those guarantees, right? Let's move ahead a little bit, right? Now, in the game, right? If we go back to the game itself, right? It's a game which is played with native currency, with with monopoly money, right? But at any point, if Arun is running low on monopoly money, right? What is there to prevent him to actually make an offer to Borun saying that I'm going to give you 100 rupees if you give me 500 monopoly currency, right? There's nothing really that can stop him from making that transaction, right? And because of this, no matter how the native currency is, what ends up happening is, if there is a demand for this native currency, then there is going to be an exchange rate that is going to get fixed up, right? There is going to be some kind of a tethering of this native currency with the actual economy, right? Just like today you can buy a lot of online likes, and you can buy game currencies using real currency, right? So there is some kind of an exchange that can be set up, and this exchange can be free floating. It really boils down to the demand that is there, right? So the other thing to observe over here, so that's one point that I wanted to make, is that the currency is, it does not necessarily operate in its own ecosystem. It is actually tethered to the real economy, right? Because exchanges can happen, right? And because there's an exchange, there is going to be an exchange rate that is going to get set up, right? The other thing is, when we are talking about ledgers, I mentioned that a cryptocurrency is nothing but a cryptographically secured ledger, right? Why is this a ledger? Because if I were to sum up all my transactions, or all the transactions that I have been part of, right, whether it is the currency that I received, or the currency that I gave to somebody, it must all add up, and the remainder is really my current value, right? So it's not a number; it is the sum total of all the transactions in my ledger, right? So that is very, very important, because with cryptocurrency, the ledger is the currency. So instead of actually giving you a token, I'm going to give you a history of that entire token, right? So just like, to give a more common example, right? Nowadays we are more comfortable with digital banking, right? But I can only imagine that all of us have had seen our parents go to the bank and getting their passbooks updated, right? So that passbook again is a ledger. It has the record of all the transactions, so that the final number, right, the account balance cannot be arbitrarily changed and cannot be a mismatch with all the previous transactions, right? So that's what we mean by a transaction history, right? So with cryptocurrencies, the ledger is the currency, right? And double spending, the problem of double spending really is, if I have a transaction, right? If I have, say, for example, I have three transactions such that I am supposed to receive 50 rupees, and then another transaction where I'm supposed to receive 100 rupees, and a third transaction where I'm supposed to make a payment of 80 rupees, right? Now, these three transactions would be possible only if the first two transactions happened and then the third transaction happened, right? Or the first transaction happened. Yeah, maybe I should take a different example. Maybe I should say that I am supposed to receive 50 rupees, I'm supposed to receive 40 rupees, and I'm supposed to pay out 70 rupees, right? In that case, there is only one ordering that is valid, right? Other orderings will create a double spending problem, right? So double spending can be avoided by forcing an order on the transaction, right? So that there is only a single truth, right? So if there were these three transactions and of me receiving 40 rupees, of me receiving 50 rupees, and me spending 80 rupees, it should not be the case that I see the transactions as A, B, and C, of plus 50, plus 40, minus 80, and somebody else sees them as in some other order. Somebody else sees them as plus 50, minus 80, plus 40, right? Because that would create two variations of the single truth, right? So I need to be able to force an order on the transactions, and that common order has to be seen by everybody else, right? So that's how you avoid double spending, by forcing an order on the transactions, right? So now the question is, how do I create this order on these transactions, right? It's great to have the ledgers. It's great to have a running total of the ledgers, right, to know what my current balance is. But how do I now ensure that the order in which the ledger was written is the single truth, right? Is really the correct order, right? So we are going to sign, right? We are going to sign the entries that we start making in the ledger itself, right? Now, we have some additional information over here, right? The first thing is that because Mala is the person who is acting as the bank, and she's the one who's making those entries. So if the person who's making the entry, implicitly they are agreeing to that entry by virtue of making that entry, right? So the first part is somehow implicitly agreeing by virtue of inserting a record. Now, the second party in this transaction needs to explicitly agree and approve that that is the transaction that they were a part of, right? How do we solve this problem, right? They also have their own R&D center for the development of technology solutions and products based on blockchain, right? And they have been, I recently saw, I think the last time when I was updating my DSC, I saw that they have Aadhaar-based signature functionality that is also available, right? And this is how we are seeing the integration of the technology infrastructures that we have created within the country, right? Similarly, several banking infrastructures, State Bank, ICICI, right, quite a few have been working with creating other kinds of identity verification systems as well. Right? So with the digital signatures, I now solved the problem that every transaction that is being put in, I can get the both parties to agree that they were part of the transaction, right? So how do I stop a replay attack? Right? How do I essentially say that okay, a record is verified by both parties, but how do I ensure that the record is not being replayed? Right? And that is why probably I mentioned this earlier that having it's the characteristic of having a good ledger is that there should be a timestamp on that ledger, right? So we can definitely include the timestamp as part of the ledger itself, right? Now this brings us to the question of how do I ensure that the timestamp that I am putting, the clock on the basis of which I'm putting this timestamp has not been tampered with, right? So that introduces a new question of trust. And this is where we typically use a protocol called Network Time Protocol, or NTP, right? It's the same mechanism that is used to synchronize various computing devices, whether it is your laptops or your mobile phones with a global time, and there is a network of servers, right, which are responsible for propagating proper time across the globe, right? And these are synchronized against what are called stratum zero atomic clocks, and this is cross-referenced with the GPS system, with the GNSS reference clocks as well, right? And then at each level of, at each stratum closer to the previous stratum, the confidence of there is significantly more confidence of having lesser drift, right? But the moment you start having a drift, if there's NTP running on your computer, it will sync up with some other server that has a higher confidence of the global time, right? So that way we can have a network of computers all agreeing that they are following pretty much the same time. There is going to be a little bit of a drift, but we may not be able to observe that degree of variation, right? For most common purposes, the individual clocks do get synchronized, right? This brings us to another question, right? Which is, we have been talking all this while about, blockchain being able to address what is called an NP hard problem of decentralized consensus, right? How we talked about blockchain bringing in trust, right? It's a cryptocurrency that has implicit trust in it, right? So where is the matter of trust coming in from, right? And where trust comes in from is by saying that even if there is an adversary trying to propagate an alternate timeline, an alternate reality, blockchain systems are resistant to that, right? So it is that's where the trust factor should come in. But these are words, right? How does that get implemented, right? So how do we get into the problem of solving for decentralized consensus? How do we get different people to agree on the same version of the truth, of the same sequence of events as being true, right? So let's take a closer look at that, right? So coming back to our Monopoly game, right? We said that what if Mala cannot be trusted with the ledger? What if she's taking a break, right? So what happens, right? So the fundamental premise is that Mala was keeping the ledger, and people are not feeling happy about her keeping the ledger. So one solution is everybody maintains their own ledger, right? If everybody is maintaining their own ledger, they are all writing all the transactions that are happening, and because all of them are writing the same transactions as they observe them, you know, things should be good. We are solving the problem of a single point of failure by distributing the information across all the different players. So that way we hope to resolve it, right? But what we have done is just change the scale of the problem, right? So instead of saying that yes, if everybody was maintaining their own ledger, they would all have the correct version of the truth. But what is there to guarantee that when a transaction happens, all of them observe the same transaction in the same sequence, right? So while a distributed ledger gives us a trivial solution in terms of saying that yes, it is possible that we can create we can have a more robust system. The problem now boils down to everybody agreeing that a transaction has happened, right? Because the moment there is a disagreement, right? The moment there is a disagreement, Arun says, yes, I paid. Borun says, no, you did not pay, right? This causes delays and inefficiencies, right? While in the context of a monopoly game, this can be settled by, over a cup of tea. If the same kind of disagreement were to happen over a property, right, I can imagine that it will not be settled over a cup of tea, right? So what we had done is we have spent a lot, society has spent a lot of time and effort in terms of building this centralized mediation mechanisms, right, with enforcement powers given to them, right? Police, courts, right? So we built this kind of a mediation. We kind of essentially built this kind of a mediation system, right? So because of this, because of all these organizations and their regulatory and bureaucratic processes were created to in order to ensure that there is trust within the society, right? And this was done more using a mechanism of deterrence and penalty, right? If you are lying, then if you have stolen, then you go to jail, right? That was how we tried to reinforce that you should not be stealing, right? But what if we have a different way, right? What if stealing or not stealing can be made more transparent, right? So it's not about two people's perspective about whom a particular asset belongs to, but a clear transfer of ownership as the transaction happens, right? If we have that record of that transaction, it essentially tells us that the ownership of the transaction changed exactly at this moment, right? So that's what we are trying to get at, right? So in a trustless system, we can imagine that everyone maintains a copy of the ledger, and every new transaction that is happening should be broadcasted to all the participants so that they can record it, right? The problem now becomes that of consensus, right? Even if new transactions are broadcast to all participants so that they can record it, will people all agree that they have received information about the same transaction? Is there consensus about a transaction, right? And as we are saying it, is there distributed consensus about a particular transaction having happened, right? So now we get to the problem of solving for consensus, right? And this is where this is where it comes out why blockchain really made it so big, right? Because any kind of fraudulent transactions would require an infeasible amount of computation, right? But before I let the cat out of the bag, let's get into where this problem is coming from, right? So first thing that we have established is every transaction is going to be digitally signed by both parties. Let us have it signed by both parties, not a problem. And it is going to be a timestamp transaction. So we have agreed on that part, right? So that a particular record, a particular transaction is secured against tampering and impersonation, right? Because it is timestamped, it cannot be replayed because there's digital signature. That particular transaction cannot be tampered with. What can happen? What can happen is that a, tra- a participant can be blocked from receiving a transaction, right? Or the transaction or the information about the transaction could itself be lost, right? Because once I receive the transaction, I can verify whether there was any tampering that was done with that transaction, right? So what if a group of players decide to band among themselves and make up hypothetical transactions that are not broadcast to the other participants, right? So that's the attack we are trying to prevent over here, right? So how do in this kind of a scenario, if we can solve for this kind of a scenario, we will be able to solve for solve this trust issue fundamentally, right? So the question is, how do all parties arrive at a consensus on the correct ledger, right? So that the transaction is deemed valid. How do they agree? If they can all see the set of transactions as they happen, then they will agree on the order of those transactions. But if a group of if a group of nodes decide to band together and stop a particular information about a particular transaction from propagating, then there will be two different orderings that will be created. One ordering which has that particular transaction and another ordering which does not have that transaction, right? That is the problem that we will try to resolve, right? So the Bitcoin protocol addresses this consensus problem using essentially computational work as the basis of trust. That is what makes it different. That is what makes Bitcoin's implementation of of the system trustless, essentially, right? So, what do I mean by this when I say that the Bitcoin protocol addresses consensus problem using computational work as the basis of trust? What would be this computational work, right? Okay, first, so we have already talked about digital signatures, right? We said that we want the digital signatures to be typically 256-bit, right? So let me go a little bit deeper in terms of how we are using this digital signature. Assuming that I have somebody's private key, right? What could I do? I would typically go in and create a message digest, right? This is a short description of something called the secure hash algorithm. And in a moment, I will come to where we are using these hash algorithms, right? Uh, the algorithm works as follows, where I have the initial 256-bit to start with. This kind of acts as my random initialization function, or this could be my private key. And then what I do is I take my input message, chunk them up into 512-bit blocks, right? For each block, I have a compression function that reduces this further to 256-bit, and then the process continues, right? So what is happening is for every time I'm iterating, the information in the previous block is essentially getting transmitted in some way or the other in a modified form into the subsequent block, right? And because at the output of every block is again a 256-bit value, the final output will also be a 256-bit value, right? Of course, I make the assumption that if my input message actually ends up, does not round up to 512 bits, right? I will create a final padded byte, a final padded block with, and align it to 512 bits, right? So, what would be the desired properties of such a secure hash algorithm? Right? A fixed length hash output, right? So I would typically want it to be a fixed value so that I can, so that I can carry forward, so that this protocol can this hashing mechanism can be iterative, right? So I want every bit to be consistently 256 bits. It's deterministic, right? It's deterministic as in I know this hashing algorithm. Right? I know this hashing algorithm, so for the given set of inputs, my the output is always going to be deterministic, right? But whenever I'm hashing something, I am reducing a 512 bits of information to 256. So I'm going to always throw away some information, right? So for example, if I have if I use modulo 12 as a hash value, and if I look at the time on the clock, right? So at any point I will get the hour count, but I will lose information about the rest of the day. Typically, hash functions are computationally very easy, right? They are very easy, so that it is easy to determine the hash value of a given input, right? They are one-way functions, which means that it is computationally easy to find the hash value of the given inputs. But given the input, it is difficult to find what values led to that hash, led to that particular output. And it is so because information has been lost while computing the hash value. Right? Typically, hash values are collision resistant, which means typically the hash space is large enough that it's large enough that I cannot I should not be able to calculate what would be two pairs of value that will lead to the same hash output, right? So it is infeasible to find x and y where hash of x is equal to hash of y, right? So it should typically be so even subsequent elements should actually be separated quite significantly, right? In case of a collision, I can create a collision resolution, which means I can have a secondary strategy in order to create a secondary hash function should there be a collision, right? There should be an avalanche effect, which means that even for one bit of change in the input values, there should be a significant number of bits that change in the output value, right? So that I should not be able to guess the input from the output itself, right? So that's where the puzzle friendliness also coming in, right? So that knowing part of the hash value and knowing the hash value and a part of the input value, it should still be very hard to find the rest of x, right? Now, why did we talk about this entire SHA mechanism, the SHA-256 mechanism, right? Because blockchain uses SHA-256 or Bitcoin uses SHA-256 as part of its blockchain implementation, as part of what is called as the proof of work, right? The proof of work, how it is computed is that if I have a ledger where I have all the transactions, right, all the transactions which are digitally signed, right, I have, say, for example, 10 transactions which have been digitally signed, so I know that they are all accurate. I am going to try and compute the SHA value for this, the SHA-256 value for this, right? So if I write it out on my left-hand side is a 256-bit representation, right, of whatever would be the SHA value. The proof of work concept essentially comes in from asking for a pattern in this output value. Remember, we just discussed that it is computationally very easy to compute the hash value of a given input, right? But the other way is not very easy. I cannot find out what should be my input value so that my output has a particular pattern, right? That becomes very difficult. And the way proof of work is defined is by saying that I need to have a pattern in this particular output. Right? What kind of a pattern? Say, for example, proof of work can be defined as saying that my hash value should be starting with 30 zeros, right? So that could be a constraint. So my question now is, for what value should I start with such that the hash of this block of transactions has a pattern starting with 30 zeros, right? Remember in my previous page, we were starting with this magic number, right? We were starting with this initial hash value and the message size. So my question now is, what should be this initial value such that the output value has a particular pattern? I have to now find this out given that my hash value has these properties, right? Where any kind of backward computation is very, very difficult, right? So how could I find this? What nouns would satisfy this condition that hash of ledger plus nouns matches this POW difficulty, right? That's my question. And there are several strategies that can be adopted. There are, I could just brute force, start with 0, 1, 2, 3, 4 and find a number, and keep on calculating these hashes until I find a number which produces this pattern, right? So that's what mining rigs do, right? Mining rigs are mining when we talk about Bitcoin mining rigs, right? These are GPU intensive computing devices, and what they are doing is they are trying to calculate this magic number, right? This number such that the output matches a proof of work difficulty, right? Just to give you a sense that how hard is this, right? This number does not look this, on paper this does not look like a whole lot, right? But how difficult really is it? Let me actually try and run this. Let me actually bring out some piece of code and see what does this really mean. I think the screen may not be very visible. Let me just try and make that a little larger. And this is some very simple Python code, right? What this code is really doing is, in order, because I want to compute those hash functions, I have just used a library called hashlib, right, which will allow me to compute those SHA values. And I have set up some initialization functions, right? And what I'm going to do is I have a binary string for saying Arun pays Mala 5,000, right? And what I'm going to try and do is compute a hash such that my target string is starting with no zeros, right? I am going to run this probably 5 times. And let's target 1, 0. So essentially what I'm looking for is a target value such that my hash value starts with 1, 0, right? So proof of work is 1. Okay, my computer decided to act up a little bit. Okay, they started to compute those values, and what it found was, let's see, it said that I found my match in try number 19. So I found a hash value which started off with 10, because I was looking, that was the pattern I was looking to match, starting with 10, and I ran this about 5 times. So each time it found me a value in 18 runs, 81 runs, 7 runs, 0 runs, and 19 runs, right? So on an average, the time taken to find, uh, the proof of work with, find a block that find a magic number that satisfies the proof of work was only 0.03. Right? Now, what would happen if I change that target a little bit, right? Supposing I now want to match, I want to have proof of work starting with 00, right? What would change? Remember, in the first run, it took me about 0.03 seconds to be able to find a solution. This time it wasn't that close, right? The average number of tries went up from about 25 to about 194. So even if one hash, computing just one hash was trivial, it does not take a whole lot of time to compute one hash, but I am having to compute on an average about 200 hashes in order to satisfy a proof of work requirement of 2, right, of 00, right? And the time went up from 0.03 seconds to about 1.29 seconds, right? What happens if I try it out with a target of 3, and I am going to iterate over fewer runs just to for the sake of time? And here again, what you can see is I'm searching with the pattern so that it begins with 000. And I think we can all conclude that it does not, it does not stop in 1.2 seconds anymore. In fact, my average runs went up from about 192 or about 200 average matches to almost 2000, right? So about from 192 to 1777, right? And the time taken has gone up from about 1.29 second to about almost 11 seconds, right? So that's an order of magnitude that it is growing at, right? Any observations on what would happen if I were to look for starting with probably 4 zeros? Let's give it a shot. And remember, all that you hear about, Bitcoin mining and all of that. This is what these machines are doing. They're just computing these hash values. They're just computing these hash values to find out for what nodes would it satisfy the proof of work requirement. And we are doing proof of work of 4, right? Not 30. So every zero that is added on for every increment in the proof of work, it is actually changing it is actually, increasing the workload requirement by an order of magnitude. Right? So if this result comes back in, I don't know, let's see, let's just give it a shot. Let's see how long it takes to actually give back a response. My guess is that it will be closer to about a minute or so, or maybe even longer. Maybe it's about a minute and a half or so. It's doing the work. It's not that it is sitting idle. It is just going ahead and crunching up those numbers really quickly. And well, I'm on a on an old computer. I am still on probably i5 computer that is running this. And even for computing the proof of work of four, it is struggling. We're still going ahead with the computation. This will give you a sense of why, where does the trust come from? Because if this is how much time it is taking to compute a proof of work of four, imagine a proof of work of five will take at least 10 times longer, right? A proof of work of six would be about 100 times longer, right? So it is already stretching me into matter of several hours. Proof of work of six would take me of the matter of months now. So a proof of work of 30 is non-trivial. It will take several rigs, several GPU intensive rigs, several days, if not months, to break it and to be able to find the nouns for one block. We are still on one run. I think you get the point, but I want this to come to a logical conclusion and find at least one solution. Remember, we were averaging about 1,700 searches for a proof of work of three. So I would have expected to have found a solution by within the top 20,000 searches, but depending on the input, it could just pick something on random. So it could take longer. And trust me, the code is fine. So we went up from about 10 seconds to about 339 seconds, right? And from about 1,700 odd searches to about 40, almost 50,000 searches. That's what that's where the power that's where the brilliance of blockchain really comes in, right? It is computationally infeasible to do these computations, right? And if you were to do these computations, it's if you were to do this computation, the cost, the energy cost, the electricity bill fundamentally of what it would take you to break the system may be more than what you're breaking it for, right? That's That's how the Bitcoin paper actually brought in computational capability as a security mechanism, right? The energy spent on the energy spent on creating that computation is what prevents the physical breach of the system, right? So that's one of the core attributes. If an adversary were to introduce an alternative narrative in a blockchain, then they would have to spend essentially, they have to recompute the entire proof of work, which means that the energy computation, the energy cost of doing that recomputation would be significantly high, right? Uh, the other that's how you brought th- that's how we address the issue of creating trust by making it infeasible to compute alternatives. And the second innovation that came in was essentially creating a chain block of transactions, right? So each block, what is now happening is it's got the previous set of transactions, right? We were talking about the game of Monopoly. So maybe every 10 transactions, we were trying to compute a block, right? What it has is this magic number, this nonce that would allow us, this block, to satisfy a proof of work requirement. And it has the previous hash, right? So it is by having this previous hash, if any of the previous blocks get changed, the hash, the next subsequent hash would no longer match. Right? Therefore, any other subsequent block would also not match. Right? So that's how we have created this chained proof of work, right? Starting with what is called as the ground zero, or the genesis block itself, right? So with when block Bitcoin initially came out, the target was that you should be able to create a new block every 10 minutes or so, and it was defined by about the proof of work was essentially started off with about 18. Today it is at about 30. Right. So how does this decentralized consensus look like today? It looks like that every time there's a new transaction, it gets broadcast to all nodes, right? Now, while it gets broadcast, let us assume that some nodes will get it, some nodes may not get it, right? Let's keep that assumption in place. But once you have a set number of transactions that can be put into a block, they gets collected, and every mining node would essentially now try to compute this magic nonce value in order to complete this particular block, right? Why is it doing so? Because the miners may have an incentive as a percentage of the value of the transaction. So that's one way of incentivizing the miners, or the miners could be infrastructure that is put in to do the mining, right? So in which case they don't have an incentive, they're part of a more private infrastructure. Once a block is created, right, this block is now sent across to all the other nodes. This information about the new block is sent to all the other nodes, and any node which was working on forming its own new block now sees that a new block has come in, so it is going to accept it in its list of blocks, and it may discard whatever block it was itself working on, right? Now, what I mentioned is that let us keep that assumption that all transmissions are not heard. All transaction information about all transactions may not be heard by all nodes. They may not be present all the time, right? For whatever reason, it may not have been heard, right? So when a block is created, we follow something called the longest chain rule, right? And in this longest chain rule, what happens is we instead of straight away letting go of the block that we were working on, we kind of keep it in a chain, right? And we have more confidence of a block being authentic if it is part of the longest chain. Why so? Because if I get two blocks which claim to have the same set of transactions, but which have the same transactions and which have two different orderings, then I'm going to put them into just two blocks and not trust either of them. But when the next block comes along and I find out which chain is it following up on, right? Then I know which chains to discard. Now, even in this case, in case of a tie, we just wait for new blocks and let them age, because the more it ages, the more difficult it would be for an adversary to create a block that has a back reference, that has also got its back references correct, right? Typically, the trust grows with age because majority of the node will produce blocks faster. And what this means is that if I have to carry out an adversarial attack of a network, right? As long as the friendly nodes can control more than 50% of the network, the probability of a new block being generated by one of the friendly nodes is always going to be more than 50%, right? A corollary of that is, if the adversary is controlling more than 50% of the network, yes, there is a probability that the adversary will be able to generate a block faster. But then what the adversary believes is the majority opinion and therefore the truth. Right? So that's a very interesting corollary that comes out of this longest chain rule, right? Otherwise, minor adversaries cannot come in and create a dent in the network, right? So that's very, very important, because this philosophy is what gives blockchain its strength, right? Its ability to withstand attacks and work in a trustless environment, right? So this is what I mean by trustless. I do not actually need to have any implicit trust on any node, right? They can issue, whatever they give me, I will have enough partial information from large enough category of subnodes that I will always be able to know the true ordering, right? And this in turn solves a very fundamental problem within a very notorious problem within computer science domain itself, called the distributed consensus problem, as is shown by the Byzantine generals problem, right? Which is about synchronizing, about agreeing on a time to attack an enemy city, where the generals may or may not trust each other. The messages that are sent between generals may or may not be true, right? The messengers could be lost. So in this kind of an adversarial network, right, the question was, how do we still go about and create trust and agree on a common time to attack, right? So blockchain is able to resolve that particular issue, right? So that's because of this capability, multiple distributed consensus problem, multiple areas where you need a solution to a BGP situation, right? Including situations of multiple people trying to write on to a database, right? Replication, a lot of those kind of situations can be dealt with blockchain-like systems. Just to summarize what we covered today, right? We talked about digital signatures. We talked about how we can create a public key infrastructure so that we can have a private key with which we can sign a digital document, so that it is guaranteed against any kind of integrity failures, right? So that any changes in the document will invalidate the digital signature, right? So we talked about digital signatures. We talked about ledger as the currency, as in the running total, the sum of all the transactions in the ledger being the currency itself, right? We talked about proof of work significantly, how we are using a simple SHA-256 mechanism and using it to create a consensus, to create a barrier for a barrier against brute force attacks, right? We are essentially using energy costs of computation as a preventive measure, right? And finally, how we are able to create these blocks, seal it with the proof of work, and chain multiple blocks together so that we are able to, we can ensure that any change would require, propagating that change all the way back to the genesis block, right? So that's where the blockchain comes in. It borrows its terminology from. And finally, how do we propagate the blocks? How do we, and by ensuring that we follow the longest chain rule, right, we are able to create distributed consensus in the system, right? So those are the major concepts that I touched on in today's discussion. I want you all to understand that when you are talking about a blockchain-based systems, it is not necessarily a system for implementing cryptocurrency, right? It can be used in multiple applications. It can be used for maintaining intellectual property, for maintaining mark sheets, for maintaining different kinds of registration information, right? So it's a more generic platform. And if you think about blockchain, it is something that compares better with immutable databases, with tokenization systems, right, with token creating systems. In general, when you build a blockchain based, when you have a blockchain based implementation of Web3, right, typically you have your the user interface, right, that can be decentralized as well, but in most implementations that is still built using Web 2.0 technologies, right? You have mobile apps and all from which you can implement all these wallets and ticketing systems and transaction systems, right? This is the viewing interface, but it is the underlying infrastructure layers, right, where the blockchain protocols are going to come in, right? This is the underlying protocol for mathematically provable decentralized verification, right? So this is where the consensus, the mining, the propagation, the semantics of the application are of the protocol are really coming in, right? And apps, DApps or Web 3.0 apps, they have several implementation architectures, from purely decentralized to one where where only the protocol part is decentralized and the UI part is more centralized. So the architecture that is suitable for you depends on where the value and the user's interface is stored, right? Are the is a user's key stored directly on their mobile phones itself and in the user interface itself, or it is stored at the exchange, or it is stored somewhere else, right? So it depends on what is the level of decentralization, and this is an architectural choice that you have to make, right, for your particular application, right? There are several configurations that are available, right? This brings me to quickly touch upon four things that I, in terms of blockchain-based systems, where are there? What is the SWOT analysis for blockchain, right? Where are there strengths, weaknesses, opportunities, and threats in this kind of a system, right? In terms of strength, blockchain brings in multiple innate capabilities, right? So there are, it does bring in encryption, but we have different ways of doing encryption. Blockchain will give us encryption. We have been seeing a lot of applications which is using blockchain primarily for its encryption capabilities. There are applications like registries, which uses blockchain primarily for its immutability characteristics, right? That once you have created a blockchain, you have entered a transaction into a blockchain, you cannot delete that transaction. You can have a new transaction saying that there is an update information, or that one of the previous transactions is deleted, is a new transaction that has to be entered in the blockchain itself. right? So there are applications that leverage the immutability part of it. Then there are applications which leverage the tokenization part of it, right? How do I use the same infrastructure to create new NFTs and all of that, right? So those are tokenization centric applications. Then there are decentralization based applications where the focus is on using the decentralization capabilities of blockchain, so that there is no single point of failure for the compute infrastructure, right? And finally, there is the distribution network, right? And with distribution based solutions, it is about not knowing where the computing resources themselves are, right? So that itself gets distributed in the infrastructure, right? So that's in terms of its strengths, which kind of applications leverage how many characteristics of blockchain depends on your architecture. In terms of weaknesses, several applications, because there is always ground truth as at genesis, which means that the first block that is created is assumed to be perfect, right? So what ends up happening with this is, if you are, for example, building the land registry mechanism of a well-planned parcel, in a well-planned city, let me take a different use case. If you are looking at a motor vehicle registry, right? So because a motor vehicle has a very finite lifetime, right? So it is possible that there was a definite point of sale when somebody bought a particular vehicle, right? But with land registries, especially in older cities, right, it may be very hard to draw a line and say that this is where things started, right? Because there could be other, that the genesis block itself cannot be guaranteed to be ground truth, right? Other weakness is that if you get in garbage, you will get out garbage. If you put in a lot of redundant information that is replicated, right, you are not going to get any value out of it, right? So that's a major challenge. You get what you put in. Third part is that it has very hard contracts. It has very, very hard contracts, which means that if there are timelines associated, if there are constraints associated with the contract, those will be followed very, very deterministically, right? So there is very almost no leeway in terms of those contracts itself. And of course, it is anonymous, which could be a weakness, which could be a strength, right? So I'm going to leave it to a particular implementation for a particular use case. It boils down to that, right? In terms of opportunities, it goes far, far beyond your currency or cryptocurrency use cases. It can be used for e-commerce, for loyalty cards, for remittances, for P2P lending. It can be used for multiple record keeping setups, right, including healthcare, title records, ownerships, votings, intellectual property. So multiple use cases around record keeping, around securities, derivatives, crowdfunding, private markets, equity, debt, all of that. A lot of companies, we may not have to issue share licenses anymore, right? We could look at initial coin offerings instead of IPOs, right? So some economies have become more liberal and allowed those use cases as a matter of record keeping. Some places we are still to have the compliance. We're going to still have the legal compliances in place, right? It does allow smart contracts, right? So that's another area it opens up. So in terms of opportunities, I think pretty much every domain that you can think of, whether it is regulation technology, whether it is loyalty technology, whether it is agricultural technologies, using blockchain-based fertilizer subsidy systems or vaccination records, right? So there are multiple opportunities that come out of it. But at the same time, from if you look at the threats of blockchain, it is an energy hog and if it is consuming energy, it is it has to be worth it, right? So it should not be storing information unnecessarily. you do not, because we are a country which still relies on a lot of fossil fuel for energy costs. At one point, I think a couple of years ago, the cryptocurrency mining was actually consuming more power worldwide than entire Pakistan, right? So it is a major energy hub, right? In terms of speed, I would still say that energy, centralized frameworks tend to do better where applicable, right? But of course, things are getting better. It's a trade-off in terms of the decentralization, the degree of decentralization, and the degree of and the speed that you need, the latency that you need. So it's an application-dependent decision whether where you place that boundary. In terms of legal framework, what parts of blockchain usage may be acceptable to a particular society, right? It's still in the gray area. Some rules are being made around it, right? But there are still quite a few challenges that have to be ironed out for a smoother implementation, right? And finally, we see a lot of blockchain-based ransomware attack on the rise, whereas previous ransomware was typically, you had the same code that was injected in. It was possible to find the release keys essentially, right? By digging into the way a particular thing was implemented. But with blockchain and with smart contracts, because the keys are specific to a particular MAC ID or a particular machine that is being targeted, right? It becomes much more difficult to generate the release key, right? So it is getting used in a lot of illegal activities as well, right? And we have to be a little bit careful in terms of ensuring that we do not succumb to these kind of challenges, right? So I think that's it from my side for today, right? Probably what we will be discussing tomorrow is a blockchain use case selection framework and quite a few use cases around where blockchains can be implemented. Look at your thought processes, right? But before I close, I would be happy to take any questions that you may have. Somebody had a question. Let me see. Sorry, Sajan, I did not notice your message earlier on. Very, very good morning, Sajan. And now almost afternoon. So if there are any questions, I would be happy to take them. Otherwise, we will meet again tomorrow. Any questions from the team? Then, if there are no further questions, then we will close the session here today. Thank you. Thank you so much, Angam. You're welcome. Right, I'll see you all tomorrow then. Thank you, everybody. Have a good day ahead.
Thank you.